Okay, so we're going to be studying polynomials, and we've actually been studying polynomials for the last week or so with our linear functions and our quadratic functions. But now we're going to look at things that have bigger exponents, like x to the third, x to the fourth, and so on within them. Now, here's the definition of a polynomial. A polynomial is of the form f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus a sub n minus 2 x to the n minus 2 all the way out to a sub 1x plus a sub 0. Now you might look at that definition and go, well, I don't really know what a polynomial is from that definition. So here's the thing to think about, and I really didn't put it here, but it's very important, where n is a counting number, or 0. Okay, so in other words, a polynomial has one variable throughout the whole polynomial, and all of the powers on our variables are counting numbers, or 0. Okay, so we can't have like x to the negative 1 or x to the 1/2. This means that there are, very important, there are no negative exponents, no x's in the denominator, because that would make it a negative exponent, no x's under radicals, under square roots or cube roots or any kind of radical, no fractional exponents. All right, so all of the linear and quadratic functions we've already studied are polynomials, because recall the linear had x to the first power, and the quadratic functions had an x to the second, and usually also an x to the first power. So they were polynomials. But now we're going to look at polynomials that have powers higher than 2. Our quadratics had their highest power as 2. Now we're going to have powers of 3, powers of 4, and so on. Okay, so we need a few definitions that you should have seen before, but we'll go back through. The degree of a polynomial is its highest exponent. The leading term is the term containing the highest exponent. So in these questions that we have right here, let's find the degree of the polynomial and the leading term. Okay, so let's notice this as we look at this polynomial. Notice all of the exponents are counting numbers. Even our x right here, remember it's always an unwritten 1. And we are allowed to have numbers by themselves, because really this number by itself has an x to the 0 power, and anything to the 0 power is 1, so we just don't write 3 times 1 right there, or 3 times x to the 0. So this is a polynomial. Let's find its highest exponent. The biggest exponent is a 5, so that's the degree. So this is degree 5. Its leading term contains that 5, and the leading term is all of this right here. So our leading term, leading, not eating, is 5x to the 5th power. All right, now let's do our second one. Highest exponent is 12. So this is a degree 12 polynomial. Its leading term is the term that contains that x to the 12th, so all of it, including the number out front, so negative 4x to the 12th. Now, that negative is very important, as we'll see here in a few minutes, so don't forget it when you're listing your leading term. Okay, now let's get a few more definitions, some that you may not have seen before. All right, so power functions are polynomials that have one term. And we've already had a few power functions. We've had x squared. Remember our library function, x squared, was just a parabola. Recall that it was a graph that looked kind of like this. Okay. And then remember from our transformations, if we put a negative in front of x squared, that flipped our parabola over across the x-axis. So it made it an upside down parabola. So made it look like this. Now we also had x to the third as a library function. And recall that was this. And if we put a negative in front of x to the third, again, it's just going to flip it over. So it would turn that upside down and make it look like this. Okay, now I've listed these particular power functions because they are very important, because they help us establish something called end behavior. And end behavior refers to how a function is behaving at its most extreme left and right sides. So let's notice, for example, x squared goes up on both the left and the right. And that is its end behavior. Negative x squared goes down on both the left and the right. Our x cubed goes up on the right and down on the left. And our negative x cubed goes up on the left and down on the right. End behavior will be determined in a regular polynomial by the polynomial's leading term. Now we'll talk about this a little bit more in a minute. So we need a couple of things before we can determine end behavior. If our leading term has a positive coefficient and an even exponent, like x squared. Notice that x squared is positive and it's an even coefficient. Then its end behavior is going to be like x squared. It's going to go up on its extreme left and extreme right side. Now it could do all kinds of stuff in between, but the ends will be going up on both the left and the right. If our leading term has a negative coefficient and an even exponent, like negative x squared, it's going to go down on both sides. Okay, again, it could be doing anything in between, but the left and the right hand sides will be going downward. If the leading term has a positive coefficient and an odd exponent, its end behavior will be like x cubed. It'll go up on the right and it'll go down on the left. And then finally, if the leading term has a negative coefficient and an odd exponent, its end behavior is going to look like negative x cubed. It's going to go up on the left and down on the right. Now, we will determine end behavior here in a second. But I want to talk about, in your exercises in the homework, it uses some notation that's a little bit difficult to understand. So let's just sort of debunk or decrypt that notation a little bit. So if we're looking at the right side of our end behavior, we're going to usually say as x goes to infinity. Because on the right side of the graph, the x values are going to positive infinity in this direction. All right, and then we will use left So on the left side of the graph, we'll say as x goes to negative infinity, because when we're looking at the left, we're thinking of the x values going forever toward the left. And then if we think of the graph going up, we're going to use the notation y goes to positive infinity, because up on our y-axis is positive. And if our graph is going down, we're going to use the notation y goes to negative infinity, because our y-axis goes to negative infinity on the downside. All right, so if we use this, this will help us a little bit when we're doing homework. And we will both do this so that it's kind of intuitive to you, and also using this notation. So let's go back up to these two polynomials we had before. We tell hidden behavior from the leading term, and we've already listed the leading term right out here. So for our first one, the leading term was 5x to the 4th. That is a positive coefficient in front of our x, and it's an odd exponent. Positive coefficient, odd exponent. Our graph is going to have end behavior that looks like x cubed. All right, so that means that it'll be up on the right and down on the left. All right, now notice what I said, up on the right, down on the left. So let's kind of decode up on the right. All right, so up on the right, we would say, notice right is as x goes to infinity, x arrow infinity, and that really does mean goes to. That's what that arrow means. So as x goes to infinity, let me change my color here. As x arrow infinity, as x goes to infinity. So that's my mathematical way of saying to the right. Our y's go up, so y goes to infinity. All right, now let's look at the other side of the graph. As we go to the left, our y's go down. So left and down. So left mathematically is written as x goes to negative infinity. So x arrow negative infinity is the symbol for left. Y goes down. So y goes to negative infinity. So this is the way that you'll be writing it in my math lab, or my open math rather. Okay, so just be aware of that. Okay, now on my test, you could write, I would be perfectly okay with you saying, as we go to the right, it goes up. Y goes up. As it goes to the left, our graph goes down. Because that's really the important idea you get out of it. And we'll see when we graph how important that idea of as it goes to the right, it goes up. As it goes to the left, it goes down is important. All right, now let's go to this one. The leading term was negative 4x to the 12th. There is a negative coefficient and an even exponent. Negative coefficient and an even exponent is going to look like negative x squared. Let's notice it goes down on both sides. So as we go to the right, it goes down. As we go to the left, it goes down. All right, so let's write that in terms of our symbols, though. As x goes to the right, that's as x goes to infinity, or x arrow infinity. So as x arrow infinity, as x goes to infinity, y went down. Okay, so y went down. Down means y arrow negative infinity. I'll kind of draw a line in between these so we know these don't belong together. Okay, now that was the right side. As we go to the left side, again it goes down. So interpretation of the left, as x goes to negative infinity, again, y went down, so y goes to negative infinity. So you will need these symbols when doing end behavior in your homework. All right? So this is our way of writing the end behavior for these polynomials. Okay, now let's get a couple of extra pieces of terminology. A polynomial can have at most n zeros, or n x-intercepts, where n is the degree of the polynomial. And a polynomial can have at most n minus 1 turning points, or maximums and minimums, place where the graph changes direction. All right, so let's go up to our two functions that we were playing around with, and let's find the number of zeros that they can have and the number of turning points. Now realize they may not have this many, but this is the most they can have. All right, so I'm going to see if I can't put a little space in here, maybe. Well, I put all these letters in there, but that's okay. All right, so our degree determines how many possible zeros we have. So 5 possible zeros. So notice our degree was 5. 5 possible zeros. And then the turning points is always one less than that. So 4 possible turning points. All right, so let's go to this one. It's degree 12, so we'll have 12 possible zeros. See if it will let me go to another. So 12 possible zeros. And then one less for the turning points, 11 possible turning